Happy Math Hour, weekly interactive math reviews for Math 1332 and Math 2412. Presented by Yvette Chuca, Ruben Carizales, Eduardo Tintos, Melinda Camarillo, and Alberto Isasi. This session will be recorded, so you may come back to it later. Also, it is recorded so others who may have missed out on today's events will be able to come and watch it. Thank you for joining us. So now at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with the information we will be sharing today. Without further ado, here is our presenter.
Welcome to Friday Happy Math Hour. Today we're going to talk about conditional and related statements, symbolic arguments, and Euler diagrams. So first we want to talk about equivalent statements. An equivalent statement have the same truth values in the final column of the truth table. So for example, if we have negation P or negation parentheses P, negation Q, and negation P and Q, if we want to show if they're equivalent, then what we can do is create a truth table. And so in this example, the last column that was created was false, false, true, false. And on the right side, the last column was false, false, true, false. And so if we compare those two columns, we can see that we got the same exact answer. So we say that these two statements are equivalent, and the symbol for equivalent is these three horizontal lines. So to show equivalence, we also have something called De Morgan's laws. And what De Morgan's law says is that for any statement P and Q, the negation of P disjunction Q is equivalent to the negation of P conjunction negation Q. So notice here that the equivalent, the negation symbol, it almost seems like a negative, right? It was distributed into the P and it was distributed into the Q, and the negation of the disjunction is going to be the conjunction. In the same way, for the second one, negation P conjunction Q is equivalent to negation P disjunction negation Q. Because we know that if we were to create a truth table, the last column for the left side and the last column for the right side would be the same, then we can always use De Morgan's law to show equivalency. So for example, it says use one of De Morgan's laws to restate the following sentence in an equivalent form. So the sentence is, it is not true that I graduated or I got a job. So first we need to identify our statements. So P is going to be I graduated, Q is going to be I got a job, and then we have or, so that's the symbol for or. And then we have that in parentheses, and we know that by the comma as well. And then we have it's not true, which is represented with the negation. So far our statement is negation parentheses P or Q. So if we apply De Morgan's law, the negation will go to P. Our symbol disjunction would change to conjunction, and then negation Q. So this would be an equivalent statement. So now we just rewrite our statement. So negation P is I did not graduate. Then we have and. Let me go again. So then we have and then negation Q is going to be I did not get a job. So in this section, we're also talking about tautologies and soft contradictions. So let's take a look at what those are. So a tautology is a statement that is always true. And so when we do a truth table, the last column, if it's all true, then we say it's a tautology. A soft contradiction is always false. So the last column of the truth table would always be false. So here we have an example. It says show that P disjunction parentheses negation P disjunction Q is a tautology. So we're going to create a truth table. So we set up our truth table. So we have true, true, false, false, true, false, true, false. And then we can start with P here, true, true, false, false. I'm going to label it 1. Then we're going to go in the parentheses, false, false, true, true, since we have negation. Then we're going to do Q, true, false, that's number 3. And we do the disjunction inside. So false, true is going to be true. False, false would be false. True, true would be true. And true, false would be true. And we can label that as number 4. So now we're going to use 1 and 4 to get the disjunction here. So we have true and true is true. True and false is true. False and true is true. False and true is true. So if you notice here, we have all truths. So that's going to make this a tautology. Now let me go back. So this would be a tautology. Okay, so for the conditional and related statements, if P then Q, that's a conditional. P implies Q. So if you see it written as P then Q, the symbol is P with the arrow Q. If it says P implies Q, then we have the same symbol, where P is called the antecedent and Q is the consequent. Okay, so equivalent forms of the conditional. If P then Q, every P is a Q. If P and Q, Q if P. So these are just different ways of writing the same thing. P only if Q, Q provided that P. So if it says Q provided that P, you're looking at P only if Q, and so on. So this table would be helpful for you to have while you're doing these problems. So example, write each of the following in if P, then Q form. The number is an even number provided that it is divisible by 2. So here is Q is provided that P. And then letter B will be today is Friday only if yesterday was Thursday. So we want to write it as if P, then Q. So first we're going to identify what P is. So P is, it is divisible by 2. And if we look at the table, Q provided that P. So after the word provided is your P. Then we'll identify Q. Q is the number is an even number. And then we're going to rewrite it if P, then Q. So if P, P is, it is divisible by 2, then now we're going to put Q. The number is an even number. Okay, let's try B. So for B, today is Friday only if yesterday was Thursday. So if we look at the table, let me go back. Now we're going to be using P only if Q. Okay. Okay, so for letter B, let me go back. So first we'll identify P. Today is Friday, that's our P. Only if yesterday was Thursday, that's our Q. So we write it if today is Friday, then yesterday was Thursday. So having the table next to you will be helpful in determining which is P and which is Q. The converse, the inverse, and the contrapositive. These are also statements related to the conditional statement. So the converse of the conditional PQ is Q conditional P. Notice that the P and Q switch places for the converse. The inverse, we're going to have the negation of P and the negation of Q. And the contrapositive, we're going to switch the Q and P, but also put the negation. So here it says write the converse, inverse, and contrapositive. If I get a job, then I will rent the apartment. So first, let's identify P. P is I get the job. Q is I will rent the apartment. So in the converse, we just switch Q and P. So if I rent the apartment, then I get the job. The inverse, we do the negation of P and the negation of Q. So if I do not get the job, that's the negation of P, then I will not rent the apartment. That's the negation of Q. And then for the contrapositive, we're going to switch Q and P, but take the negations. I do not rent the apartment, then if I do not rent the apartment, then I do not get the job. Okay, so these are all equivalent statements. And so if we look at the truth tables, if we were to make truth tables, then we can see that the converse and the inverse are equivalent, and the conditional and the contrapositive are equivalent. Determine whether the given statements are equivalent. So here are my statements. And so we want to check to see if they're inverses or not. So if I live in El Paso, then I live in Texas, right? So that's going to be, let's say that's P, conditional Q. And I live in El Paso is your P. I live in Texas is your Q. I do not live in Texas, so that's negation Q. Negation Q. And then I do not live in El Paso. That's negation P. Okay, so here we have the contrapositive because we switched the Q and the P, and then we have the negation of it. So the second statement is the contrapositive of the first. Therefore, the statements are equivalent. And we can see they're equivalent from our table here. So this was our statement, and the contrapositive, they're the same, so they're equivalent. Okay, so now let's see. Oh, so letter B, if A is equal to B, then A times C is equal to BC. If A does not equal B, then A times C does not equal BC. So first, even though this has letters, we can still identify our P. So let's say this is our P, and this is our Q. So this statement is P and Q. So we have if A does not equal B, so that's negation P. Then A times C does not equal B times C, that's negation Q. So that's going to be the inverse of the first. Therefore, the statements are not equivalent. And again, we can see that in our table. So we got the inverse, but the inverse is only equivalent to the converse, not the original statement. Therefore, that's why they were not equivalent. Okay, so now we're going to jump to something a little bit different. Symbolic arguments. This is from 3.5. And so an argument consists of a set of statements called premises and another statement called the conclusion. An argument is valid if the conclusion is true whenever all the premises are assumed to be true. An argument is invalid if it's not a valid argument. Okay, so for example, if Einstein was human, then Einstein was mortal. Einstein was human, therefore Einstein was mortal. So my first premise is if Einstein was human, then Einstein was mortal. The second premise is Einstein was human. Conclusion, therefore Einstein was mortal. Once we have identified the premises, we can give them symbols or give them some letters here. So H is going to represent Einstein was human. M will represent Einstein was mortal. So our first sentence, if Einstein was human, so that's our H, Then Einstein was mortal. So that's going to be our M. So we can write it as H conditional M. Then our second statement, Einstein was human. So that is H. So that's H. Then our conclusion, therefore Einstein was mortal. So mortal was M. So this is our statement. So the three dots here represent the therefore. Once we have our statement written in symbolic form, then we want to show if it's valid or invalid. Okay, but I guess before we do that, let's practice rewriting something in symbolic form again. So she gets on a plane, that's our P, or she will regret it, that's R. So that's our first premise. She does not regret it, that's negation R. Therefore, she got on the plane. So our three dots and the P. So to determine the validity of the argument, we already did step one. We wrote it in symbolic form. Then we're going to construct a table, a truth table, that shows the truth value of each premise and the truth value of the conclusion for all the combinations. If the conclusion is true in every row, then we say the premises are true, then the argument would be valid. If it's false, then it's invalid. So let's go back to our Einstein problem. So we have our first premise. Well, first we have our two statements, H and M. Then our first premise, H conditional M, is going to be, so we have true, true, with the conditional is true. True, false, with our conditional is false. False, true is going to be true. And false, false will be true. Then our second premise is true, true, false, false. So we just copied our H. And then our M, we just copy the M, true, false, true, false. And so we want to look at, we can see here that row 1 is all true. And then the rest of them, row 2, row 3, and row 4 are all false. Okay, so we're going to say this is valid. Now what you can also do is you can set it up in a different way. It might take a little bit longer, but it works. So if we have H, M, so that's your first premise. And, so I'm going to use a symbol for and, the second premise, and this is all together. Then the conclusion, M. So if you make a truth table for all of this, the last column, which would be right here, then you would have, that would determine if you have a tautology, which would make it a valid statement. So for example, H conditional M, we saw that that was true, false, true, and true. And then H here is true and true, false, and false. So if we have the and, it would just be true here, because I'm looking at true and true. False, true would be false. True, false would be false again. So this is false and false. And then M is true, false, true, and false. So now I'm looking at true, true would be true. And then false, false would be true. And this was false, true would still be true. and false would be true. So if you notice here, we get all true, so that makes it a valid statement. But to avoid doing the entire truth table, then we can just focus whenever these are true and your conclusion is true. And that was from the statement right here. If the conclusion is true in every row of the truth table in which all the premises are true, the argument is valid. Okay, so here all my premises are true and the conclusion is true. And those are the only ones we consider because that's when the premises are both true. So this method here is a lot shorter than having to do the whole truth table. So let's practice another one. Okay, so if it rains, that's R, then the game will not be played, negation G. It is not raining, negation R, therefore the game would be played. So that would be therefore G. So now we want to, we wrote it in symbolic form. Now we're going to look at the first premise here. So we have a negation, so we can add negation G, which is false, true, false, true. And now we're looking at the conditional. So true with false is false. True with true is true. False with false is true. False with true is true. So that's our first premise. Our second premise, we have negation R. So instead of true, we write false. True, we write false. False, we write true. False, we write true. So the only ones we're going to consider is where the premises are both true. So that is the last two rows here. So we say, okay, this is true, true, and true. So that's a good thing. And then true, true, and false. Since we got a false here, then this will make it invalid. In order for it to be valid, this would also have to be true. Okay, the next thing is the Euler diagrams. So many arguments involve sets whose elements are described using quantifiers. So these were from the first section. So all, some, and none. So if we have all P's are Q's, that means that the P's, we would draw a circle to represent everything in P. And since all P's are Q's, we can draw a circle around the Q. No P's are Q's means that the two circles are separated. Some P's are Q's. We're going to have interlocking circles, so they have a common area. And then some P's are not Q's. These are still interlocking, but the one that we're looking at are the P's that are not Q's, represented by that dot. These are called Euler diagrams. So for example, use an Euler diagram to determine whether the following argument is valid or invalid. All college courses are fun, so we're going to draw a circle for that statement, and then we'll continue drawing the circles. So all college courses are fun. So here's my college courses. And since they're all fun, I draw a circle around the fun. This course is a college course. So the only place that I can put a dot for the second statement is going to be inside of the college circle. Since that's the only location that I can do my second premise, now we can look at the conclusion. This course is fun. So my dot is the course that we're talking about. It's inside the college circle, which is also inside of the fun circle, making this statement a valid statement. Let's look at this one. All fried foods are greasy. Okay, so let me just start over here. So all fried foods are greasy. So we would have a circle for the fried foods. And then we're going to have a circle for the greasy foods. And since all fried food are greasy, that means that the fried food has to go inside. So that's my greasy. And then all greasy foods are delicious. That means we have to draw another circle And since all greasy foods are delicious, that means that my delicious circle has to be around the greasy food. So this is my delicious circle. And then it says all delicious foods are healthy. So since they're all healthy, then I have to draw my healthy circle around the delicious circle. And the conclusion, there's no way I can redraw this. This is how it has to be drawn. All fried foods are healthy. So if you notice here, the fried food circle is inside of the healthy circle. Therefore, it makes this statement valid. And that's the picture. Let's try this one. All M's are N's. So here's my M circle. And all M's are N's. So the N circle has to be around the M circle. And then it says, no N's are P's. Okay, so what does that mean? Our P circle has to be away from the N circle, right? So I can write it over here. Here's my P. And the question is, can I rewrite the M so that somehow it touches the P? Or it says to, in this case, we're going to do a conclusion. So what can we conclude from here? So all M's are N's, no N's are P's. So what does that have to do with our M's? Okay, so we can see that none of the M's are going to be P's. And so these are some examples of Euler diagrams. And that is it for today. Thank you.
Thank you so much, Ms. Chuka, for presenting today. Thank you all for coming and being such a wonderful audience, and we definitely hope to see you again soon. So join us next week. Look at the flyer, and you'll see that for Math 1332, we'll be covering XM2 review, and for Math 2412, Law of Sines and Cosines. Hope to see you all then. Have an amazing weekend. Bye.